In this last video for our first chapter on integrals, we're going to look at a technique for evaluating certain types of integrals. We should make a note here that whereas for derivatives we always have a rule that allows us to take a derivative, either it's the power rule, the product rule, the quotient rule, the chain rule, or some combination of those rules. For integrals, we do not have anywhere near the same kind of simple rules that we have for derivatives. We do have a power rule, so if we're integrating or taking the antiderivative of x to the n, we are going to add 1 to that power and then divide by that power, and you can see that if we go back the other way and differentiate this, we bring the power down, the n plus 1's cancel, we reduce the power n plus 1 to n, and we're back where we started. We should, on the power rule for integrals, add a plus c here, plus c meaning any constant c, because when we differentiate any constant c, we get 0. So the power rule for integrals gives us actually infinitely many results. It's not just this part, it's any constant c. However, we can't go any further than that. There is no product rule, there's no quotient rule, there's no chain rule. However, the rule that we are going to develop next, the technique we're going to develop next, the substitution technique, is actually a variant of the chain rule. So let's start off by characterizing the general way to write the substitution technique. It may not be the way that you understand this best. You may understand it best by an example, but let's try and do it using the most general language. So an integral of the type where there is a composite function, and that composite function is multiplied by the derivative of the inside function, right? So this is the inside function's derivative, the g prime of x. When we have that structure, a composite function multiplied by the derivative of the inside function in the composite function, we can use this, what we call a substitution technique, and we will always substitute for a new variable u the function g of x. So let's see by example how that would apply with this particular integral. So do you see that this part here, the x cubed plus 13 to the 5th power, is our composite function. Let's tag it COM. Let's actually write out composite. So the part in the brackets, the green brackets, is our composite function, and it's also true that this is the inside function and that this part right here is the derivative of that inside function. So if we follow the structure outlined in the general case, we should let u equal the inside function g of x. After we identify what u is, we differentiate that u. So let's use this notation for the derivative of u with respect to x, and that's 3x squared. But we actually want to write that in a different structure. We want to bring the dx over to the other side and write du as 3x squared dx. So let's box this in. And then let's go back to the integral that we're trying to calculate, and notice that what we have boxed in is actually this part that we boxed in of our original integral. So let's tag that part as du. Now let's look again at the part of our original integral that was in the green square brackets, and notice that that is u to the 5th power. So So this right here, x cubed plus 13, is what we assign to the variable u. It is raised to the 5th power, so everything here in the brackets, x cubed plus 13 to the 5th, is u to the 5th. And so what we've got now is a much simpler form of the integral. So let's transform our integral. The part that was in the blue box here becomes du, and the rest of the integral is u to the 5th. And so if we put everything in one color, we're just integrating u to the 5th du, which is the same as integrating x to the 5th dx. We just add 1 to the power and divide by the power. So we get u to the 6th over 6 plus c, this power rule that we talked about for integrals. Right, this rule right here. So if we write that in, replacing u with x cubed plus 18, we see that we have our result, x cubed plus 6, or x cubed plus 18 raised to the 6th power divided by 6, and then we add a plus c. So there's our result. So let's do another problem of this type where we don't have everything so intensely tagged up. Let's see if we can do it a little bit with a little bit cleaner approach. So here's the integral that we're trying to determine. And let's notice that for this inside function right here, this function right here is inside prime. Well, it's almost inside prime. And it turns out it's close enough that we'll still be able to do this. So let's set up what u is. Now, we want our du to be this part of our integral. And we can see by looking at what we have here for du, that's not quite what we want it to be. What happens if we change the right side to be what we want it to be? Well, that would be, we could do that if we divided the right side by 3. But if we divide the right side by 3, we have to divide the left side by 3, so let's do that. Right, we got what we wanted. We wanted the right side of this expression here to correspond to what we have in the integral, and it does now, but it's not du like it was in the other case, it's du divided by 3. It turns out that we can generalize this. We don't have to get exactly du, we just have to get du multiplied by some constant, or of course divided by some constant. What's the rest of the integral? The rest of the integral is u to the 5th, and so our integral becomes this, which integrates to u to the 6 over 6 plus c, and then we substitute back in what u is, x cubed plus 3x squared plus 18, and we see that we've gotten a result, x cubed plus 3x squared plus 18 to the 6th power over 6 plus c. Let's do one more example of this type, and then that should cover most of the types that we'll encounter of substitution technique. So it's a little bit more disguised in this integral. This turns out to be, it's clear that that's our inside function. It's not as clear that this part right here in the denominator is our inside prime, so let's see how that works. So let's set u equal to square root of x plus 6. So we let u equal the inside function. We rewrite it with a fractional power. So it's easier to differentiate. We differentiate, we write it back in the square root form, and we see that we do not have exactly what we want. We want to have dx over the square root of x, but what we have is dx over the square root of x multiplied by 1/2. So what are we going to do? We're going to do what to both sides? Right, you see that we'll multiply by 2. Right, so the thing we want, dx over square root of x, becomes 2 du. So let's tag this as 2 du, and then everything else is sine of u. So we have this much simpler integral, sine of u du, and it turns out that whenever we have a constant inside an integral, such as this 2, we can bring those constants outside of our integral. So this is a simple integral in the sense that we haven't talked about the integral of sine before, but we're looking for a function whose antiderivative, or that is the antiderivative of sine. What function has derivative sine? That would be minus cosine, right? So the antiderivative of sine is minus cosine, and the 2 remains, and then we substitute back in for u square root of x plus 6, and we get our answer. So in both the second and the third example, you saw that we didn't exactly get du. We had 2 du in this case, and in the previous case we had du over 3. These problems that we just worked are problems in the text if you want to follow along with them. This one is that we just worked is example 1 on page. So this one that we just worked is example 1 on page 111, and the previous one that we worked is actually example 2 on page 112. And then the first one that we worked is actually the preview problem that's on page 111. So we've covered 3 examples of the substitution technique. This first one is kind of messed up now because we did so much tagging. This one, and I hope you've seen enough examples that you are able to apply this technique correctly to the homework problems.